Okay, I think we can start, Thomas, right? What do you think? All right.
Okay, yeah.
So, welcome everybody to another session of the IVM meeting. Today we have Jakub Hruby from the MagLab in Tallahassee. Jakub is a EPR spectroscopy who trained in the lab of Peter Nagebauer in Czech Republic in Brno, where he did high field EPR on graphene hybrid materials. And during this time, he did a couple of internships abroad. So he was visiting student in the lab of Roberta Sessoli and Matteo Mannini in Florence. And also he went to Stuttgart to work with Joris van der Lageren. Now he's at the MagLab. He has been since March 2022, and he's in a postdoc in the group of Stephen Hill, and he's working on high field EPR on lanthanides and for quantum information technology. And today is presenting exactly his results on this topic. So Jakub, floor is yours.
Right. So thanks for the introduction to us. So today it's a little bit, so this platform or format allows me to go a little bit more broader and don't have to hurry up that much. So for this IVEM EPR seminar, I prepared this topic about tunable clock transitions in lanthanide complexes for quantum information technologies. It's a collaborative work from our side, the MagLab, and the chemists in Berkeley and the Naval Air Warfare Center in California. So let's get started. So I'll start a bit vice versa, or from the end. So in the beginning, the quantum information processing or technologies. So nowadays it's really a hot topic. So if you have these classical bits, the linear technology we use every day in our PCs, phones, works on the classical bits 0 or 1. The idea of a quantum bit is that we could use the quantum property of superposition of states. So this is a depiction of block sphere with the same 0 and 1, but we're also able to access or have the superposition, which is depicted by this point on the block sphere, which can be written by so this is like wave function. So we have here the T1 spin lattice relaxation and T2 spin relaxation times magnetization. So the main idea would be the use of superposition, and for some specific time, let's say T2, we could make our space bigger and use it for the quantum computing. So if, let's say, 1 qubit is quite useless, but the main power is if we add up more qubits together. So in the case of 2 qubits, we can write the wave function as a linear combination, and here the alpha, beta, these unique parameters are necessary in order to describe our system. So in other words, we need more parameters to fully describe our system, and this is where the information can be stored. In the end, it's about the probability. So the quadrants of the probabilities need to be 1, and at the end we measure again 0 or 1, as in the normal case. But as mentioned before, the advantage is in having more of the qubits. So in the case for 3, we need 8 parameters to fully describe the system. So it's 2 to the power of n scaling, where n is number of qubits. And this is I guess most of you already know these basics about the quantum information, but it's a bit the introduction. And so qubits, potential to use the superposition, and to the power n scaling. So at the brink of this quantum era in 2000, it was formulated by De Vincenzo that there is a list of, let's say, necessary requirements in order to construct a meaningful or useful computer. So the first is scalability and well-characterized qubits. So our approach, or what we're focused on, is the molecular approach. The qubit state initialization could be done by pulse TPR, and the long coherence times, T2. Our focus is the clock transitions. This I'll describe later. Here I'll also mention if you have any questions you can ask during the presentation, but it might be that you ask and I will explain the stuff on the next slide, so it can be also done at the end. There's also other requirements which we're not directly addressing. You need a self-quantum gains, and you need cubic specific measurements, and there's much more, but I guess it's good to see what's our pitch or our field. So this is just again how we measure in EPR. So it's a relaxation of magnetization. So you apply external magnetic field, and then you apply pulses, and you see how the magnetization relaxes. So here in the blue one, we have the T1, and here in the red we have the T2, the spin-spin relaxation time. So in the MagLab, what's our, let's say, the flagship, or what we hear the most is the system called Hyper, which is 94 gigahertz W band, operating at 3.35 Tesla for G2. Our main, this is Manoj, my colleague, who I guess it's roughly 1 month ago, he described the system more in detail. So it's a design based on the one from St. Andrews of Graham Smith. So this is like a twin, and we use it for measurements of these T1, T2 measurements. It's our workhorse in this area. It's a really nice instrument. So here, this is quantum computing market cap. It's from this Quantum Insider, and this is just not exhaustive, but overview of this booming quantum field. I've also attended this APS March meeting in physics, and pretty much 70% of everything was quantum. So it seems to be a new thing to go. So when, I don't know, 10, 15 years ago it was graphene, now everything is quantum. So this is just a list of companies that have something to deal with quantum. So here, our research, or what what I'll present, is more closely related, or the inspiration is from this ion trap. And you can see that many of these companies, you know, from the normal instruments like cryogenics, the Oxford, Keysight, everything is focused on everything is quantum nowadays. So the inspiration, or what we're not really mimicking, but what we're investigating in our molecular systems. So the idea of ion trapping is that you have a positive, let's say, ion, and you apply this. This is a quadrupolar ion trap. You can see a picture here. You can buy it on eBay. This is linear quadrupolar ion trap. It was there for like $250. So it's achievable stuff for most of us. So the idea is, here we have a positively charged ion, and here on these poles we apply electric field, which then constrains, or let's say this is for the 2 AC cycles. So here you have plus minus, here you have minus plus. So you you apply AC current, and you keep the ion in the place. For this ion trapping, there's been a Nobel Prize in 1989, and the use for quantum computation was presented by Sirac-Zoller in 1995. Quantum computations with cold trapped ions. So who's the players, or who's the companies who were exploring this approach? So it's this Quantinuum, which is Honeywell plus Cambridge quantum computing, and the IonQ. What's common for these two companies? They use the Ytterbium 1+ with this electron configuration. So it's a fully occupied F shell and 6s1. So there's one unpaired electron. It's giving this isotope has 1/2 nuclear spin number. So there's also some other approaches. For instance, this barium. This is since 2021. So there's also different candidates, but pretty much the Ytterbium 1+ is the system explored. And what I managed to get from their website is they have up to 10 qubits today. So what is our idea? So we can make this analogy to the molecular system. So we're working with this Lanthanide, which is a lutetium 2+ in this lutetium Cp-IPR4 ET. It's a neutral compound, and it's a not normal oxidation state for lutetium. So the normal is lutetium 3+. There's no unpaired electrons. There are no EPR signal. Only up to recently, it's been showed by the group of Bell Evans that it's possible to reduce to the lutetium 2+. So this reduction creates this one unpaired electron, which we're able to probe in the EPR. So here you can see this green is the one lutetium electron. This is let's say depiction of the DFT SOMO for the DZ² orbital plus S orbital. So here you can see this orbital cloud, and here I put this partial charge, let's say on the ligands. So the idea is pretty similar, like in the ion trap, that if we are able to change the bending angle on the ligands, we're able to somehow squeeze or imprison the electron in the S shell. And this is so for 90 degrees, the S character is lower than for the 180 here. So this is just a depiction of how it would be. So increasing axility leads to increasing S orbital character in these compounds. And by this chemical fine-tuning, we can promote the clock transitions, which leads to longer spin relaxation times, and this could be useful in quantum computing. So this is the chemistry behind these compounds. So what was the evolution of these lutetium 2+ compounds? So in 2019, there was this first example. As you can see, the G is not that close to S character, and the hyperfines for this lutetium compound was say 1.1 gigahertz. This was 2019, and then last year, by my colleague Krish Kundu, so they're investigating the series of lutetium and lutetium and lanthanum compounds. Here it's just for lutetium, So you can see that this Lu OR3, it had already 1.92, and the hyperfine splitting was 3.5 gigahertz. So this all is by the increasing S character in the compounds. And this work, they're pushing it further to the S values of 2. This already last year, this led to the T2 enhancement of order of magnitude at the clock transitions. This I'll show a little bit later, the clock transitions. And the hyperfines are around 4.3 gigahertz, which is large for molecular compounds. So a pure s orbital would be G222. The hyperfine interaction, let's say the main 2 contributions could be the magnetic dipole, or in this case, it stems from the Fermi contact interaction. And the bigger hyperfine leads to bigger clock transition. So we were investigating the series of these lutetium compounds with different bending angles. The difference between the angles is not that big, but this is the EPR signal always versus magnetic field. The measurements are at 5 Kelvin and 240 gigahertz. This is continuous wave EPR. The black line is experiment and the red one is simulation. So you can see these 8 characteristic lines, which stems from the spin 1/2 and the electron spin 1/2 and the nuclear spin 7/2 for this compound. So you can see the here in the table this comparison. You can see the increasing bending angle leads to increase in the values of the hyperfine. So this is the lutetium compound series. Here, what is important to know that all of them are extremely sensitive. So they're air sensitive, moisture sensitive. So it's not that easy to perform these measurements. And so we are also investigating the linear case, but we're still analyzing the data. So how does a spin Hamiltonian look for such a compound? So here, this is the middle one here. So as I mentioned, spin 1/2, nuclear spin 7/2. So we have 8 transitions. So the G values, the G perpendicular and G parallel. This is the first, the electron Zeeman contribution. Then we have the nuclear Zeeman contribution, the hyperfine, and also the nuclear quadrupolar interaction. This interaction is rather small, but it's crucial, very important in these analyses, because it leads to this small shoulders and also the features in between the spectra, or between the main transitions. So this is the nuclear quadrupolar contribution, and this gives us the whole spin Hamiltonian, what we consider. What was also interesting in this compound, so the normal, or let's say the major isotope is 175, but in this case we're also to see this 2.6 abundance of the 176 lutetium isotope, and you can see here, if you zoom, it's also visible here on the right side. You can see that there's also a slight hint of the, or let's say, contribution of the other isotope. So this is sometimes you have to look also into the detail. and analyze the background. So I didn't mention these clock transitions yet. So the clock transitions, this is the approach of prolonging the T2. So here, this is just the scheme. Here we have frequency versus applied magnetic field. And the clock transition is, you can imagine, as avoided energy level crossing. So here I have the, let's say, the spin down. And here at the clock transition, this is the avoided energy level crossing, because normally we go here. But here we have the derivation is zero, derivation of frequency by the magnetic field, and it stems from the non-diagonal perturbation of the Hamiltonian. So we have the diagonal Hamiltonian plus the non-diagonal perturbation, and this will lead to the creation of clock transition. So in the first order, the derivation of frequency by the magnetic field goes to zero, and this increases the coherence time by lowering magnetic noise. So the transition frequency here is less sensitive to local magnetic induction. It's also in the second order. Second derivation is proportional to 1 over the let's say the magnitude or the gap, and so the bigger clock transition leads also to reduced second order sensitivity. So let's say the bigger clock transition, the less sensitive to magnetic noise it is. So we want higher frequencies, higher clock transitions. So the perturbations I mentioned, what could be the origin, can be zero field splitting or hyperfine interaction. So in our case, or this work, the origin is the hyperfine interaction. So here this is the energy versus magnetic field for the lutetium compound, and here you can see this overlay of the EPR spectrum with the energy level, the levels plot from isospin, and here you see these eight transitions. These are the allowed EPR transitions: delta ms equals 1, delta mi equals 0. But so here, where's the clock transitions? Hold on, Jacob. I don't see any clock transitions. So you have to go to the simulation to the low magnetic field regime, and here you can see that there's a few transitions that have this behavior that they the derivation goes to 0, and here, for instance, this delta transition between levels 7 and 9 would appear at 11.3 gigahertz. So the clock transitions lie in the low magnetic field regime for this compound, for generally every compound. So here, this is overview. So you have your molecular system, which can be zero field splitting or hyperfine. So for the zero field splitting, the widely studied, or let's say the studied system, was this holmium polyoxymaltide. So this was the in 2016, and this is a review 2019. So here there's a T2 in microseconds, and this is different transitions, different magnetic fields. And here you see this divergence of T2. So this is how you see that there is a clock transition in your measurement. So you go to the place in the magnetic field where you think the clock transition, and you vary your frequency. This is illustrated here. So you go in your setup to 23.5 millitesla, and then you vary the frequency, and you can see that it jumps up. So this is how now there's a clock transition. So in this case, it was measured on X band, and this led to the increase roughly one magnitude, 1 order of magnitude, T2. There's also this example of the low spin cobalt. on S-band. This was I think 3.66 gigahertz. This led to the increase roughly 7 times the clock transition. And this last year's lutetium work from Krish was also measured on X-band, was also roughly order of magnitude. So here you see the normalized eco-spin envelope intensity versus magnetic field. You see the low magnetic field regime from on the X-band, and here this transition is let's say long-lived population, or you can see that for 20 microseconds it's still visible, whereas the other peaks are not visible anymore. So this is how you know it's your clock transition. So this is just a few example. There's not that many let's say systems where it's been studied so far. This I'll explain on the next slide why. So the current status is these clock transitions, they take advantage of great chemical tunability, as was shown in this. You can tune the ligands, you can play with the, let's say, with the ions. It can be transition metal, it can be lanthanides, probably also actinides. The great advantage is the scalability, because it's a molecular system. So if you imagine you could put it in some metal organic framework or something scalable, it will be the work done. You don't need to care about anymore. So it leads to the significant T2 enhancements. What's the current downsides, or let's say the challenges to tackle, is that you can also measure, let's say, frozen solution, but ideally you want to have a single crystal. There usually might be air or moisture sensitive in the case of lanthanides, and you need to have magnetic dilution of your system. So you need to find some host. There's also the question of quality of EPR spectrum. So usually you measure your CW or eco-detected field sweep, and then you simulate it, you get your spin Hamiltonian, and based on these parameters, you have your low field prediction of clock transition. So if you don't have quality EPR spectrum, the prediction will not be great. And also if your clock transition matches the prediction. So if you do the experiment to look for the clock transitions, what's the match with the prediction? This is also a challenge to tackle. So some final thoughts. Most of these things are addressable. So nowadays, the biggest challenge or obstacle is that, as I showed you, there's clock transitions at frequencies that are not standard for EPR. So you have these dedicated S, Q, V, W bands, and let's say if you have clock transitions at 25.5 gigahertz, then it's not really addressable. So there's some microwave limitations, also instrumentation bandwidth limitations in these pulsed experiments. But on the other hand, it's also great room for improvements. Or nowadays, these electronics, femtosecond lasers, arbitrary waveform generators, solid state amplifiers, quantum cascadelators, or these, let's say, new additions or over the years developed techniques can help you to make it much more addressable. And here, this is so when I was a kid, I was using this GSM, the 2G, which operated at these frequencies. Like nowadays, pretty much, I guess everyone has this 5G phone, which is already, let's say, 20 times, 30 times higher frequencies. So the trend is going higher frequencies. The sensors, adaptive cruise control in your car, 77 gigahertz. These mobile networks, everything is pushing to the higher higher frequencies. And this is also, I guess, a great for the EPR or microwave technology, because with let's say every new phone sold, there's a, you know, it's kind of funding the research on these solid state amplifiers and everything. So I guess it's optimistic. We'll be able to tackle and measure much more. Just for now, we have to, let's say, match the technology we have with the chemistry we have, and so either fine-tune the molecules that we can measure them, or develop machines that be able to measure these clock transitions in a larger scale, and this will really push up the research. So in the end, I would like to acknowledge the Hill group, namely the Krish Kundu, who was kind of pioneer in this works. Then also Steve Hill, people from California, the Berkeley, Dan, Ryan Murphy, and Jeff Long, and in the Naval Air Warfare Center, the Randall McLean and Ben Harvey, and also the fundings that are supporting all these researches. So at the end, if there are any questions, here I also put so we're hiring postdocs, students. So if someone would be interested to work more on these clock transitions, working with these nice high power, high frequency pulsed instrumentations, you can scan the QR code that will